Welcome back, infrastructure admins. Today, we're diving into a highly focused explainer titled NCP-MCI 7.5 12.4 Synchronous Replication 0 RPO. So picture this. You're running a massive financial trading platform, or maybe a hospital record system. In those environments, losing even a single second of transactional data isn't just an inconvenience, it could literally mean millions of dollars gone or critical patient care delayed. That is the intense, high-stakes realm of 0 RPO. Today, we are laser-focused on Objective 12.4 for your certification, and we'll be working entirely within the baselines of AOS 7.5, AHV 11.0, and Prism Central 7.5. Look, for mission-critical workloads that absolutely cannot afford to lose a single byte of data in a disaster, synchronous replication is the undisputed gold standard. But deploying it? Well, that requires adhering to incredibly strict architectural constraints, and you've got to know those constraints inside and out to pass this exam. Let's get into it.
Here is our roadmap for today. First, we'll talk about why 0 RPO matters. Second, we'll walk through some concrete examples. Third, we'll dive into synchronous recovery scenarios. Fourth, we'll flag those common exam traps you need to dodge. And finally, we'll wrap up with the key facts you absolutely must memorize.
All right, part 1, let's lay the foundation and talk about exactly why 0 RPO matters.
Before we get too deep into the weeds, let's make sure we're on the exact same page with a couple of fundamental terms. First is RPO, or Recovery Point Objective. That's simply the maximum acceptable amount of data loss measured in time. The second is RTT, or Round Trip Time, which is how long it takes a signal to travel to a destination and back again. Now, synchronous replication is uniquely designed for workloads where the RPO is exactly 0 seconds of data loss. But here's the catch. This magical 0 RPO is fundamentally bound by the uncompromising laws of physics. It's only possible when data is written synchronously to two separate sites over a physical network with unbelievably low RTT. Ultimately, you are fighting against the speed of light traveling through fiber optic cables. Distance is the ultimate enemy here. The further apart your data centers are, the higher that latency climbs, and the harder it becomes to guarantee 0 data loss.
Let's break down the actual mechanics of how this works. To get that literal 0 data loss, every single write has to be committed to two separate physical locations at the exact same time. It introduces what we call a write penalty. When a guest virtual machine issues a write command, that primary application is frozen for microseconds. It goes like this. Step 1, the write traverses the network. Step 2, the recovery cluster receives it. Step 3, it's committed to storage at that recovery site. And Step 4, an acknowledgement is sent all the way back over the wire to the primary cluster. Only then is the application finally told, hey, your write was successful. Now, this absolutely guarantees continuous data availability during a site failure, but it strictly dictates that the network must immediately handle and acknowledge both writes without hesitation. If your network hiccups, your application performance instantly hiccups right along with it.
Moving into part 2, walkthrough and concrete examples. Let's see how this plays out in the real world. Let's compare a perfectly supported deployment with a guaranteed exam trap. Imagine a critical financial database spanning an AHV metro setup between two on-premises data centers. They're connected via a robust fiber link with sub-5 millisecond latency. This works beautifully. It's exactly what Nutanix intended. But contrast that with a major exam trap, attempting synchronous replication from your on-premises environment to a Nutanix Cloud Clusters, or NC2, availability zone. You cannot do this. It is strictly unsupported for DR solutions. Why? Because latency over public cloud infrastructure can be unpredictable, and that completely breaks the ultra-low RTT requirements needed for synchronous writes. For those hybrid cloud scenarios, you've got to stick to asynchronous or near-sync replication.
Now, here's a massive exam anomaly regarding the snapshot sequence. Even though the active replication is continuous to achieve that 0 RPO, the protection policy itself still schedules discrete recovery points. When you configure the policy, it takes a baseline snapshot immediately. From then on, it takes snapshots every 6 hours. But here is the critical why you need to know. Because the data is being replicated instantly at the storage block level, these recovery points are strictly crash consistent only. Think about it. Taking an application consistent snapshot requires VSS integration or quiescing the guest operating system. That pausing process introduces latency, which would completely break the 0 RPO synchronous link. Connecting those dots, understanding that you cannot get application-consistent snapshots using a sync schedule because it disrupts continuous writes, is absolutely key for the exam.
Okay, part 3, synchronous recovery scenarios. What happens when the infrastructure actually breaks? Test questions love to grill you on when manual administrative intervention is required versus when a failover happens completely automatically.
Let's consider a severe split-brain scenario. What happens if there's a complete network failure in the recovery cluster, or the connection is totally severed between the primary and recovery sites? Well, the synchronous replication simply breaks after a timeout period. The entities will keep running happily on the primary cluster, but your ability to automatically recover them is gone. You see, automatic failover in a network isolation scenario is incredibly dangerous. Both sites might think they're the active primary, which leads to massive data corruption. And that is exactly why Nutanix requires you, the administrator, to step in, make the judgment call, and manually break the replication.
You really need to internalize this comparison, a storage outage versus a network outage. Like we just covered, a severed network connection requires your manual intervention to prevent split-brain chaos. But imagine a backplane failure on your primary storage. The host is up, the network is perfectly fine, but the disks are gone and the storage goes inaccessible. In this specific scenario, the system safely knows it can fail over automatically. The replication breaks until you either fix the primary storage or manually enable it on the recovery side. But the failover itself? Zero human intervention required. Knowing exactly when the system takes the wheel versus when it waits for your manual command is a must-know.
Section 4. Common exam traps. These are the rigid facts and edge cases test writers love to use to trip you up.
Be extremely vigilant about these limitations. First, you are restricted to a maximum of exactly one synchronous replication schedule per protection policy. Just one. Why? Because restricting it prevents you from accidentally oversaturating that highly sensitive, low-latency link with multiple conflicting streams. We already established that recovery points are crash-consistent only and that NC2 is totally unsupported. But let's unpack a couple more edge cases. If you're using VMs with physical GPU resources, you cannot restore those entities at the recovery cluster if it has incompatible GPUs or no GPUs at all. The VM will just fail to boot. And finally, if an entity is actively protected with a synchronous replication schedule, you are fundamentally restricted from reverting it.
Don't overlook this prerequisite. It's a huge gotcha for scenario-based exam questions. The storage container name of your protected entities must be an identical match on both the primary and recovery clusters. For example, if your workloads sit in a container named self-service container on the primary site, an exactly named container, matching capitalization and all, must exist on the recovery side. A single typo means the replication setup fails entirely. In the real world, this is why we rely on automation or copy-pasting instead of manually typing container names. The exam will absolutely try to trick you with a slight typo in a multiple-choice option, so keep your eyes peeled.
Finally, Part 5. Key facts to memorize. Let's distill this down to what you absolutely need to carry into the testing center.
5. If you remember one number today, make it 5. 5 milliseconds is the absolute maximum round-trip time latency permitted between your AHV clusters for optimal synchronous performance. Remember that write penalty we talked about? Every single write command has to travel this distance and back before the application can move forward. Anything beyond this 5 millisecond threshold causes severe application performance degradation. If you're pushing past 5 milliseconds, you need to be architecting a near-sync deployment instead, which handles a 1 to 15-minute RPO. And just to support this strict requirement, Nutanix also dictates that you maintain adequate bandwidth for peak write periods and have a fully redundant physical network between the clusters. Let's lock these 4 pillars in because they define the entire 12.4 objective. 1. Latency must be strictly under 5 milliseconds RTT. 2. Snapshots are strictly crash-consistent only. 3. You are limited to a maximum of 1 sync schedule per protection policy. And 4. There is zero support for synchronous replication to an NC2 environment. Burn these 4 pillars into your memory. If you know these cold, you will easily navigate the trickiest scenario questions they can throw at you.
Before you head into exam day, I want to leave you with this architectural challenge to chew on. Since a protection policy only supports 1 synchronous schedule, how would you design a multi-site deployment that leverages that single 0 RPO link to your closest data center while simultaneously routing asynchronous or near-sync schedules to a tertiary site or an NC2 instance for maximum global resiliency? Figuring out how these schedules safely coexist is the mark of a true Nutanix expert. Map that architecture out on a whiteboard, and you'll be well on your way to crushing the NCP-MCI 7.5. Thanks so much for joining this explainer, and good luck!